Hello, ladies and gentlemen. In the following minutes, I will present you some results of fatigue experiments we performed on an aluminium alloy to detect the crack initiation time and crack initiation site using a multiple potential drop measurement. The DC potential drop method is often used in fatigue experiments to measure the crack length. With a power supply, a constant current is conducted through a specimen and the potential is measured in the region where the crack is initiated and the crack is propagating. From this potential, the crack length can be calculated by using the Johnson formula or another mathematical expression. The sensitivity of the potential drop method depends on the crack length and is rising with the crack length so that it's suitable for measure the crack length of long cracks and the crack propagation rate. The potential measurement is also very sensitive to temperature fluctuations, and therefore this method is only partially suitable for crack detection where we deal with very short cracks. In a first approach, the potential drop is proportional to the cracked area. But when you get in a deeper insight, the potential drop depends on the densification of potential lines. And therefore, the potential drop depends on the position of the potential probes and the position of the crack. This we can use to detect the crack initiation site when we use multiple potential probes on our specimen. Perhaps we can also detect the crack geometry with this method. We used for our investigations the aluminium alloy 7475, a clad sheet material with a thickness of 2.85 millimeters. We produced SEN specimen with a width of 20 millimeters and we introduced a notch with a length of or with a depth of 1 millimeter. We used also laser cuts to produce secondary notches within the notch root to get the crack initiation at defined position within the crack. And we used 3 different crack initiation sites. The first one is in the center of the notch root, then in the edge of the notch root, and at about a quarter thickness in the notch root. The potential drop measurement was performed on 3 positions: on the front side, on the back side, and the narrow side of the specimen, as you can see here in this sketch. We used copper wires with a diameter of 0.2 millimeters. They were laser welded directly on the specimen surface in a distance of about 1.5 millimeters away from the notch root. The measurement of the potential drop we performed with amplifiers of our control electronics, and so we get all 3 measurements at the same time and can record the potential curves during the fatigue experiments. The fatigue tests were performed with a constant force of 9 kilonewton and overloads were introduced in distinct intervals with 18 kilonewtons to mark the crack front on the crack surface. From the measured potential, we calculated a relative potential by dividing the actual potential value by the mean value of the first 20 cycles. From this relative potential, we calculate also quotients by dividing the relative potential from the front side by the relative potential of the narrow side, and the same for the potential measured on the back side of the specimen. Let's start with the first example with a center crack in a specimen. You can see here the crack surface of the specimen. The crack was initiated at this laser notch on the left side, and you can see on the crack surface the lines produced by the overloads to mark the crack front. The crack initiation was at the secondary notch, overload interval 10,000 cycles, and you can see here the measured potentials, front, back, and on the narrow side. To compare the crack surface with the measured potential, here the overloads are marked by colored lines. When we look on the run of the potential, we can see that the potential on the front and the back side shows a nearly identical increase, and also the quotients are absolutely identical. The increase of the potential at the narrow side is a little bit smaller compared to the two other potentials. In the first cycles, you can see an increase of the potential that indicates that a crack is formed nearly in the first cycle and it's propagating into the specimen. The potential quotient in the first cycles is nearly 1, so because all the three potentials are nearly identical. When we go to a second specimen with a center crack, there is a little difference observable in the run of the potential. Here you can see that the potentials, especially after 30,000 cycles on the front and the back side, differ a little bit. In the first cycles they are nearly identical, so there is no great difference, but you can also see the crack initiation takes place in the first cycles. The quotients we calculate from these values, they differ a little bit. So you can see the quotient from the back side is a little bit higher than the quotient on the front side, and that starts at about 8,000–9,000 cycles in the experiment. These differences are due to the asymmetric crack front. You can especially see it here in the orange line here. There are significant differences in the crack front on the back side and the front side. When we have an edge crack, the potential drop looks quite different. The potentials are clearly separated from each other, and even in the first cycles. The quotients we calculate from that differ also, and you can use the change in the quotients on the front and the back side for indication of crack initiation. So you can see that here it starts to differ, and here a crack must begin to propagate, and you don't need to look on the increase of the potential drop. Let's now have a look on a specimen where we forced the crack initiation at a quarter of the thickness. You see again the overload marks with the overload interval, in this case of 7,500 cycles. The potential curves look clearly same as in the case of the edge crack. The both potential at the front and the back side are clearly separated from each other, even at the beginning. So we can say that there is a crack initiation at about 4,000 or 5,000 cycles. That can be better seen in case of the potential quotients. Here you can see clearly begin of the separation of the two curves in the region of about 5,000 cycles, which clearly shows that there is a crack formed and this crack is propagating. For longer cracks, both curves are nearly parallel to each other, showing that the inclination of the crack front on the surface is nearly the same and doesn't change for longer cracks. Again, another specimen with a quarter crack, overload interval again 7,500 cycles. nearly the same as in the specimen you've seen before. And there's one difference you can see in the potential quotients, that for longer cracks, both curves get closer to each other, and this clearly shows that the inclination of the crack front gets smaller, and therefore these both potential quotients get closer to each other. To compare all our different cases for crack initiation, you see here the three different crack surfaces, the potential quotient curves, and we can clearly separate the crack initiation in the center of the specimen from an edge crack, but between an edge crack on the right side and a crack initiated at a quarter of the thickness, the differences are not very pronounced, but perhaps the difference here in the potential drop are a little bit different. To conclude this experimental findings, the multiple potential drop measurement allows the determination of the crack initiation site. We can determine the crack in early stages very soon in the experiment. Differences between the crack initiation at the edge and at a quarter of the thickness are not significant, but they are visible, and temperature effects can be eliminated, and we can get information about the crack front form, but we need a better mathematical description, and therefore we want to develop a vector-based model where we can also determine the crack size and crack form. Thank you very much for your attention.